A particle of mass m is fired horizontally through a block of resistive gel. The resistance to motion is mkv squared newtons, where v meters per second is the speed. The particle enters the gel at a speed of 1000 meters per second and 100 of a second later exits the gel at a speed of 10 meters per second. Show that k is 99 divided by 10. Okay, let's get a picture of what's going on. Let's consider the particle when it has moved some distance through the gel. Initially, just before it enters the gel, its speed is 1000. So let's consider its speed sometime later while it's moving through the gel. Let's say its speed is v. Now there's a force on it in the horizontal direction that opposes the motion. So all resistance forces oppose the motion, just like, say, the friction force. Well, friction force is nothing other than a resistance force. It's due to a particle being in contact with some other object. Now the magnitude of the resistance force depends on the speed. It actually depends on the square of the speed, and that's true for many resistance forces. For objects falling towards the Earth's surface, for example, when we want to consider a resistance, we will find that a resistance varies as the speed squared of the particle. So if we call R the resistance force, we can see that R is proportional to the square of the speed. So that means that if we double the speed, what happens to the resistance force? It goes up by a factor of 4, because 2 squared is 4. Of course, we could triple the speed. If you imagine 3v instead of v, then R becomes 9r. So if we triple the speed, the resistance force goes up by a factor of 9. So the resistance force goes up very quickly as the speed increases, because it's proportional to v squared. It's also proportional to the mass. Well, that's a given in this question. That's fixed. Okay, so that's the particle. K is a constant that depends on the materials involved, the shape of the particle, and also what the gel is made of, stuff like that we don't need to know about. K is some positive constant, actually, because we're dealing here with the magnitude of the resistance force. So the magnitude is positive, of course, the magnitude of any vector. So we want these three quantities to be positive. So K is some positive constant. So that's just a little bit of background on resistance forces. They all tend to have this form. By the way, we are assuming that the only force acting on the particle is the resistance force. So the particle has been fired, and as soon as it leaves whatever firing mechanism that it is fired from, the only force acting on it is the resistance force of this block of gel. Of course, we could be doing this near the Earth's surface, and then we have the force of gravity acting on the particle, but that's actually perpendicular to the motion of the particle, so we can just forget about that force. But to make things even easier, we could imagine this block of gel in outer space, far away from any gravitational field. So the only force acting on the particle is the resistance force. Now the first thing that we need to get is the acceleration of the particle. The resistance force is not constant, so the acceleration will not be constant. We need to apply Newton's second law, which tells us that the resultant force on any particle is the mass of the particle times the acceleration of the particle. Well, this is the magnitude of the resultant force, equals m times the magnitude of the acceleration. So the only force that's acting on the particle is the resistance force. So the resistance force is the resultant force, and its magnitude is mkv squared. So we can cancel these m's, and we can see that the acceleration does not actually depend on m. It doesn't matter what m is. The acceleration is kv squared. Now it's important to point out that what we have here is the magnitude of the acceleration. I said the magnitude of the resultant force is mass times the magnitude of the acceleration. Now we really have to bring in the fact that we're dealing with vectors here. So the direction of the acceleration is very important. The direction of the resultant force is to the left. So it's actually negative if we take directions to the left as being negative, which we usually do. So directions to the right are positive. That means that the resultant force F is negative, which in turn means that acceleration is negative. The acceleration is in the same direction as the resultant force by Newton's second law. So to emphasize that we are talking about magnitudes, we should really put vertical lines here. So this is a positive quantity. We said before that k is a positive constant. V squared is always positive. So we are indeed talking about a magnitude here. So, but the acceleration vector is pointing to the left, so we have to stick a minus sign in front of kv squared. So the particle is decelerating, and the deceleration is kv squared. Now we know that acceleration is given by the rate of change of the velocity vector with respect to time, where v is a velocity vector, and that's minus kv squared. So this quantity has to be negative for a particle that's decelerating or slowing down. Now before we answer the first question, even before we look at the first question, we are going to attempt to solve this differential equation to get the speed v, well, the velocity v, as a function of time. So we separate out the variables. V's on one side, t's on the other side. The k is just a constant, of course, a positive constant. We get the integral of both sides. Now, this is an easy integral to get. This is v to the minus 2. So when we integrate v to the minus 2, we add 1 onto minus 2, minus 1, and we have 1 over minus 1. So we get minus v to the minus 1. And on the right hand side, we get minus k times t, integrating the constant with respect to time. So we just multiply the constant by time. Now we can do this in two ways. We can consider indefinite integrals, integrals with no limits, and put our constant over here. The constant from both sides goes to the right hand side, and then look at the boundary condition. So at t equals 0, the particle enters the block of gel and its speed is 1000. So we could set t equal to 0 and put v equal to 1000 and solve for c. Well, actually we have two constants of integration here. But still we could do it this way, but I'm going to do it the other way, which involves definite integrals. So we've seen this done two ways in previous videos. Okay, so the initial time is 0. If we go back up here, we will see that the final time is 100 of a second. So t runs from 0 to 0.01. And at t equals 0, the speed v, well, the velocity I should say, is 1000. It's plus 1000 because the velocity vector is pointing to the right in the positive direction. And at t equals 0.01, 100 of a second later, the velocity is 10. Now, we have an equation here with only one missing quantity. That's k, the constant k, which, as I said before, depends on the materials and also on the shape of the particle entering the materials, like how much area is pressing against the gel and so on, stuff like that, as I said, we don't need to know about. Okay, the upper limit is 10 here. Then we have a minus sign. We have this again with 1000 in for v. We put the upper limit in. Minus sign. We have this quantity again, minus k times lower limit, which is 0. Okay, 10 to the minus 1 is 1/10. 1000 to the minus 1 is 1 over 1000. We get 0 for that term. If we get a common denominator of 1000 here, we have to have minus 10,000 over... I'm sorry, we need minus 100 over 1000. Gives us minus 1/10. And 1000... And what do we need here? Well, we just need 1 over 1000. I should have just done this in the calculator, but anyway. Alright, so here we get minus 100 plus 1 is 99 over 1000, and we need to divide that by, well, we get minus 99 over 1000 divided by minus 0.01. Or we can multiply both sides by minus 100. Okay, so we get a positive answer. So we get 99 over 10. That's what we had to show. Use the fact that this integral here can be written like this. Actually, we covered this type of integral in previous examples. to show that the length of the block of gel is 10 over 99 ln of 100 meters. Okay, so to get the length of the block of gel, we have to consider the distance travelled, s, by the mass, or the particle. So, again, we can do what we did in previous videos for the acceleration. Get the acceleration involving not time but distance. So we are going to try and get s as a function of v, or v as a function of s actually. We want to get v now not as a function of time but v as a function of s, because we know that v is 10 when at the distance that we are interested in finding. Okay, so we can set v equal to 10 and solve to find s. We could have this the other way around actually. We could have s as a function of v, and what we're after is the distance s when v is 10. This is what we want. The distance travelled by the particle when v is 10 is the length of the block of gel. So let's go back over this again. We did this twice before. We put ds in the denominator because we want to bring in distance, but we need to compensate, of course, by multiplying the numerator by ds. Then we see that ds dt is just the speed v, and we have v times dv ds. So this is another way to write the acceleration. The acceleration is v times dv ds. Okay, so this ds dt here is the speed. It's distance ds divided by time taken dt. Well, an infinitesimal distance ds divided by the infinitely small time taken dt. Now, of course, you don't have to use the letter s. You could use the letter x for distance. You know, it doesn't matter. Okay, we have a separable differential equation, like all the equations in this course. Bring all the v's to one side, so divide both sides by v squared. And then multiply both sides by ds. So now all the v's are on one side and s's are on the other side. The k is just a constant. You can leave the k over here, or if you want to, you could have brought it here, and you just have a 1 here, but it makes no difference. Next, we integrate both sides. We've straightforward integrals to solve here. Now we could consider indefinite integrals, forget about the limits, and get v as a function of s. You know, we'd have a constant of integration and we'd use the boundary condition to get rid of it. We could do that, but I will actually use the definite integral approach. So we are interested in the distance ranging from 0 when the particle just enters the block of gel, s is 0, to the final position, s, when the speed is 10. So s is a function of v. And v ranges from an initial velocity of 1,000 to a final velocity of 10. Okay, so this is the picture. So when t is 0, s is 0. So the particle is at the origin. And also v is 1,000 when s is 0. And when the particle emerges at some distance s that we will determine, the speed v is 10. So the position, not at 0, the position s when v is 10 is what we're after. Okay, if you integrate 1 over v, you get ln of v, and integrating 1 with respect to s just gives us s, of course. Now we know what k is. It's 99 over 10. Well, that's just 9.9, of course. We plug in the upper limit. That's the distance s when v is 10. Minus sign. We have minus ks again, but plug in the lower limit, which is 0. Well, that's just going to be 0. Okay, if you want, you can write ln 10 minus ln of 1,000 as ln 10 over 1,000, which is ln of 1 over 100, or ln of 0.01. Okay, using the fact that ln a minus ln b is ln a over b. And then divide by minus 9.9. Now we have to show that s is this thing here. But I mean, you can just work this out in your calculator and compare it to the result of this thing here. Well, if you want to be fancy, I'll just rewrite 0.01 as 1 over 100. ln of 1 over 100 is ln 1 minus ln of 100. ln of 1 is 0, so we get minus ln 100 on top, and we have minus 99 over 10. So when we divide this by minus 99 over 10, it's the same as multiplying by 10 over 99. So minus signs go, and we get the required form. A train of mass 200 tons moves along a straight level track against a resistance of 400 v squared, where v meters per second is the speed of the train. Notice again that, like in the last example, the magnitude of the resistance force is proportional to the square of the speed. That's true in general for resistance forces. The engine exerts a constant power of p kilowatts. The acceleration of the train is 8000 minus v cubed divided by 500 v. We want to find the value of p. Now I just want to go back over work and power. So consider a particle moving a very small distance, ds. We could also call it dx. I'll use ds here because we often use s for distance. Let's suppose that the component of the force in the direction of motion is F. So over this tiny distance, the force is constant and has magnitude F. The work done by the force on this particle is the magnitude of the component of the force in the direction of motion, which we said is F, multiplied by ds, the distance that the object moves. Now we are working it with differentials here because we might find that the work varies depending on the work over different intervals is different. The force may change and so on. Okay, so this is just work done equals force times distance, but we're just considering an infinitesimal distance here, ds. So the work done is infinitesimally small, it's dw. Okay, how do we get the rate of work done? Well, we divide by the time taken for the particle to move from here to here. So we must divide this side by dt. Notice, by the way, that when we talked about force, the work done by this force on this particle, that the mass of the particle doesn't come into it. It doesn't matter what the mass is. The work done by this force on the particle is independent of the mass. Now, the rate of doing work, the rate of change of W with respect to time, is known as the power. So we just call that P. And notice here we have ds over dt. Well, that's the rate of change of distance s with time. Distance over time is velocity. The units of power are joules per second. Okay, because work is measured in joules, time in seconds, of course. So joules over second. We are told in this question actually that the power is constant. So V may vary at each instant, F may vary at each instant, but whatever happens, F times V has to be constant. Let's see that that's the case. Okay, let's look at the forces acting on the train. The resistance force points in a direction opposite to the motion of the train, which is to the right. So directions to the right are positive. We've the force of the engine on the train, which I will call T. I'll make T a little bit longer just so the diagram is more readable. Of course, T has to be at least equal to the resistance force. The train is to stay moving to the right. Alright, the resultant force then has to be to the right. I'll use capital F as I normally do for resultant force. Now we can apply Newton's second law. The magnitude of the resultant force F is the mass of the train, which is 200 tons. That's 200 times 1,000 kilograms, multiplied by the magnitude of the acceleration, which is this quantity here, 8,000 minus v cubed over 500 v. At least this should be the magnitude, so this should be positive. Well, even if it's not, it could be negative for some values. If we won't worry too much about this. We can think of this as a vector equation actually. So this is the resultant force vector is the mass times the acceleration. This is a vector. So let's sum the force vectors acting on the train. Well, the vertical vectors cancel out because the train is on level ground. So we add the horizontal vectors. So t is pointing to the right, it's positive. This vector is pointing to the left, so it's negative. Okay, let's relate t to the power of the engine. By the way, this F is not the same as this F here. I use this F to talk about a force on a particle. The work done by a force F on a particle as it moves a distance ds. But here the force in question is T. Okay, we're dealing with the power of the engine. So we need to consider the force on the train due to the engine. That's T, the traction or tractive force. So if we go back to the idea of work, it's the work done on the train by the engine. So we have to consider the power done on the train by the engine, by this force T, not by the resultant force. Now we have to be careful here. I said earlier that P has units of joules per second. Now 1 joule per second is 1 watt. So that's written W. So the units of P are the watts. But the constant power of this train is P kilowatts. So we need to convert this to watts. There are 1,000 kilowatts in a watt. P kilowatts is 1,000 P watts. So we have to use the correct SI unit, T will be measured in newtons like all the other forces. V is measured in meters per second. So these are the SI units for force and speed. So power then will come out to be in watts, not kilowatts. The power of our train is not P watts, it's actually 1,000 P watts. So we should have 1,000 in front of this. Now, the quantity on the left hand side is in watts. And these quantities are in their normal SI units. So everything is okay. Remember, we are told that P is some constant that we have to determine, so that when we go to solve the equation, P should come out to be a number. It should not involve V, which is a variable. Alright, so we need to plug this thing here in for T, and hopefully P will come out to be some number. Okay, next we will multiply both sides by V. So we'll cancel this V. On this side we will cancel this V. When we multiply this term by V, we will get 400 V cubed. Now notice that V disappears completely from this equation. So when we divide across by 1,000, we get 3,200. Now the units of this are of course kilowatts. That's what we were given, that P is in kilowatts. Part 2. The train travels a distance 69.07 meters while its speed increases from 10 meters per second to v1 meters per second. Find the value of v1. So here's the acceleration of the train that we were given. Now, the acceleration as we know is dv dt, but we want to write the acceleration in terms of v and s. Okay, we want to bring the distance s into this problem because this problem involves a distance. So as we've seen before, we know that A is dv dt. If we multiply above and below by ds, we get ds dt, which is v times dv ds. So this is what we need to use for the acceleration. The next step is to separate the variables, so v is on one side and s is on the other side. So we will multiply both sides by the reciprocal of this quantity. So we'll have 500v times v, that's 500v squared, divided by 8,000 minus v cubed. This is multiplied by dv, and now we just have 1 on the right hand side. But next we will multiply both sides by ds. So the ds will disappear on the left hand side. We have ds times 1, which is ds on the right hand side. The next step we know is to integrate both sides. Now we will get a pair of definite integrals, so let's consider the limits on these integrals. The speed increases from 10 to v1, so the lower limit here will be 10, so v is 10, and the upper limit will be v1. So what's the time corresponding to the speed of v? What's the distance corresponding to a speed of v? Okay, so we want the distance travelled while this change of speed occurs. So we'll say the initial distance is 0, and we have some final distance s, which will be a function of the final speed v1. So this value 0 down here is the displacement of the train when the speed is 10. So we set that to 0. So this is the initial position of the train. Now notice in this integral that if we differentiate the numerator, we get a constant multiple of the denominator. The derivative of v cubed is 3v squared. Okay, so the power of the numerator is 1 less than the power of the denominator. So we let u equal the denominator, get the denominator into a single term, differentiate u with respect to v to get minus 3v squared, interchange these to get a substitution for dv. Next we plug in u and plug in for dv. These v squareds cancel as expected, so we get an integral with respect to u. So we pull out the constant factor minus 500 over 3, we get the integral of 1 over u, which is ln of u. And we can plug back in for u, we can plug back in 8000 minus v cubed. Okay, we apply our limits to this thing. We're integrating from 10 to v1. On the right hand side we're integrating 1 with respect to s. Well, that just gives us s, as we know. The upper limit is the position of the train when the speed is v1, and the lower limit is 0. Well, we just plug the upper limit in and we just get the position at v1, and the lower limit gives us 0, of course. Actually, I forgot to mention that we know what this is. This is 69.07. So we need to solve this equation for v1. Okay, we plug v1 in for v and we get this here. Then we have minus sign and then this thing again. So we have minus 500 over 3 ln of 8000 minus the lower limit cubed. 10 cubed is 1000. Notice here that we can pull out a common factor of 500 over 3, and if we do that we're left with ln of 7000 minus ln of 8000 minus v1 cubed. That's the same as ln of 7000 divided by 8000 minus v1 cubed. So that's the rule. Ln a minus ln b is ln a over b, where a is this thing here. So we have a single log term on the left hand side. That happens because we had this common factor that we could pull out, and then we have a difference of log terms. Okay, so the next step is to multiply both sides by 3 over 500. Okay, now we need to raise e to the power of both sides, because when we raise e to the power of the left hand side, we just get the argument of the log function, and we must raise e to the power of this number. So this is what we get to 5 decimal places. Now, to get v1 cubed, we can interchange this number with this denominator. Okay, we're nearly there. We just have to subtract 8000 from both sides, change the sign of both sides, and take the cubed root. We get an answer of 15 meters per second.